In January of 2016, Bobby Ray Simmons Jr., a hip-hop artist better known as B.O.B., set the social media world to Twitter by making the claim that he believed that the Earth wasn't a sphere, but rather a disk. Somewhat predictably, there was immediate criticism of the position from any number of circles, including the famed astrophysicist, science communicator, and media personality Neil deGrasse Tyson. Dr. Tyson engaged in a bit of back and forth with B.O.B. before the whole thing blew over as the yearly 24/7 news cycle moved on to other, more substantive matters. While there were those who bemoaned both the state of the American education system and/or a climate of modern anti-intellectualism, the more likely explanation of B.O.B.'s views has to do with the old adage that there's no such thing as bad publicity. I'm sure that for the 15 minutes of fame his statements provided, B.O.B. received a huge number of internet searches for and downloads of his music, something I suspect may have been very important in whatever business negotiations he might have been engaged in at the time. The kerfuffle, however, exposed, I think, a much more interesting trend in our thought. One of the surest ways to brand a person as ignorant or anti-intellectual is to suggest that they believe the Earth is flat. It's a slight that doesn't merely suggest just a lack of intelligence, but rather an actual embrace of willful ignorance and backwardness. In a time when satellites daily show the Earth's shape and rotation when tracking the great weather systems that travel around the globe, clinging to a model of the Earth most clearly espoused by the writings of Homer, a poet and dramatist dead 27 centuries, seems rather ludicrous. However, if you ask people when humanity finally became aware of the Earth's true shape, they will give you an answer that may be nearly as inaccurate as the flat Earth misconception itself. Many will tell you that it was Portuguese navigator Christopher Columbus who first claimed to know that the Earth was a sphere when trying to sell a business venture to the newly crowned monarchs of Spain, Ferdinand and Isabella. The truth is that most of the world around the Mediterranean knew the Earth's true shape by the time of Plato, some 1800 years before the man who sailed the ocean blue went to the Spanish court with his hat in hand, offering a chance to break a papally granted monopoly on the spice trade. The question we wish to answer in this episode is how such a thing was known. What lines of evidence were there that the Earth was a sphere, and how were they arrived at? Once we address these, we'll spend a little time looking at ways used by different astronomers not only to confirm the Earth's shape, but also to make measurements of its size. Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a many-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery. Series 3, Finding Our Place. Episode 6.1, Supplemental, Rounding the Earth. So, figuring out the shape of the Earth is not as easy a problem as one might imagine. The biggest reason for this, as is often the case in science, is in overcoming our bias to rely on our most direct perception and observation. If one goes out into a large field or onto a short grass prairie or savanna, say, thinking of the sky as a dome isn't really all that difficult. The ground, however, isn't nearly so easy. In the cases where the terrain is particularly flat, say on a boat in the ocean, one can be convinced that the horizon is circular, but not that the surface upon which the vessel is floating is somehow higher than the horizon. Where there is terrain, often even slight changes in elevation will thwart an observer's ability to ascertain shape. As one travels in a direction, the horizon slides forward, and so the perception of a flat Earth is reinforced. Such would have been the case for societies of hunter-gatherers who first considered such ideas, and in the archaeological record, we see many examples of such flat Earth cosmologies. Whether the Earth is a flat shield, a turtle's back, or an island surrounded by water, this is the picture developed by many of the peoples based on what they saw around them. However, as once roaming tribes and clans began to settle down, develop agriculture and husbandry, and begin to refine their astronomical pictures, they start taking more careful observations. While these are usually made to refine the agricultural calendar, they also provide other data that the casual observation of surroundings would have missed. In time, this data would have forced a reevaluation of the picture of a flat Earth into something else. Now, we don't have a written record of that process for the most part. Lost in the mists of antiquity are the writings of some natural philosopher in ancient Greece or astronomer priest in Babylon or China who might have first argued that this or that observation was a proof of the Earth's sphericity. Instead, what we are left with are the arguments made by later writers such as Aristotle, who offer forth several lines of evidence so well known that they can be stated without much debate. So what were the arguments used in the Greek world to support a spherical Earth? There are 4 common arguments cited in support of the claim. The first 3 of these are from direct observational data, while the 4th is derived from a combination of observation and Aristotle's physics. The first 2 have to do with ancient Greece's maritime and colonial heritage. First, when one stands on the shore and watches a ship sail away, what is observed is that the whole of the ship is the first to disappear, and then the sails, and then the tops of the masts. When a ship is sailing towards the observer, the exact opposite occurs, with the tips of the mast appearing first and the hull last. This can only be the case if the Earth curves down and away from the observer. As such, this would eliminate any flat shapes for the Earth, though it would still allow for both a cylinder and a spherical shape. The second piece of evidence is that as one travels north, either by land or sea, the height of the celestial North Pole increases, and as one travels south, new constellations will appear above the horizon on their paths from east to west. Now, if one did this on a single line alone, a cylinder-shaped Earth would also produce this observation. However, the same observation could be made either from Sicily up through the Italian peninsula in the west, and through Mesopotamia and up to the Black Sea in the east. That these observations were the same fit a spherical Earth explanation much better than they did a cylindrical one. A third line of evidence had to do with observing lunar eclipses. If these eclipses were caused by the moon moving through the Earth's shadow, the fact that this shadow could be observed to be curved during the initial and final stages of the eclipse was an indication of a curved surface of the Earth. Again, as in the case of the second observation, if one were to apply this in the case of a single eclipse, one might be able to say that the Earth could be a cylinder. But when the same observation is made over hundreds and hundreds of eclipses, as was the case in the Babylonian or Chinese eclipse records, one would think that sooner or later one of the shadows would be a straight line from the edge of the cylinder. Once again, a spherically shaped Earth best explains that effect. The final line of evidence came from Aristotle, who said that the natural motion of objects is in a straight line towards or away from the Earth's center, depending on their composition. He claims that this would press the Earth into a round shape. Additionally, as falling objects travel identically in all locales, all of the sites must share a common center, which could only be the case if the Earth was a sphere. These first 3 lines of evidence were enough to convince the Pythagoreans and later Plato, who taught that the Earth was a sphere without much proof. It is Aristotle who gathered the arguments and stated them clearly in his work On the Heavens. As this work would be one of those that survived the fall of the Western Roman Empire, it would have been available to any person with learning throughout the history of the West. While it is possible that many of those common people who did not have access to such learning might have reverted to the flat Earth model during the medieval period, it is very unlikely that the learned did so. When the writings of Aristotle began to make their way into Europe through contact with Moorish Spain in the 10th and 11th centuries, it is very clear that anyone who could have read would have known Aristotle's arguments and accepted them. This is a theme we'll return to later in the episode. What should be noted here is that these are somewhat philosophical arguments, and while certainly based in common sense reasoning, they don't involve much rigorous measurement to establish their claims. The earliest numerical estimates we have for the size of a spherical Earth date to the time before Aristotle, who claims a number of about 400,000 stadia from maybe 350 BCE, and Archimedes, who cites a value of 300,000 stadia, possibly using the work of a philosopher Decaarchus from around 300 BCE. The first person we have an actual record of doing the calculation is an astronomer and mathematician at the Library of Alexandria by the name of Eratosthenes of Cyrene. Actually, Eratosthenes, who lived from about 276 to 194 BCE, was an amazing polymath who studied just about every topic under the sun, including geology and geography, biology, languages and history, along with astronomy and mathematics. He would eventually become the head of librarian at Alexandria. Colleagues jealous of his broad proficiency of knowledge and application occasionally referred to him by the second letter of the Greek alphabet, beta, implying that he was the second best at everything he did. A better description of him, however, was that he was a first-rate scholar whose intellectual interests took him into the stunning array of fields where he made significant contributions. In this spirit, he was also known as Pentathlon, after the ancient Greek Olympic competitors who were well-rounded enough to excel in each of the disciplines in the games. The one for which he is best remembered, however, involves the report of shadows in the town of Syene near the modern city of Aswan. Syene is very nearly on what is known as the Tropic of Cancer, 23.5 degrees north of the equator. Because of this location, on the day of the summer solstice, the sun would have been directly overhead for an observer there. At Alexandria, north of Syene, the sun on that same day would have been high in the sky, but not at the zenith. This would have meant that a gnomon in Syene, i.e. a perfectly vertical stick, would have cast a shadow on that day in Alexandria, but it would not have in Syene. Eratosthenes was reading a report from Syene when he came across the mention that when a person leaned over a well on the date of the solstice, the shadow of their head would block the light of the sun from reaching the water at the bottom of the well. Eratosthenes realized that this could only be the case if the sun was at the zenith at that time of day. Now, if he had not thought that the Earth was a sphere, he might have tried to puzzle out how it could have been the case that this measurement or this observation was true, and thus come to the conclusion of the Earth's surface as being curved. This is something that the Chinese will do during the Ming Dynasty with a series of gnomons that they build from north to south. Now, given that he's working some 75 years after Aristotle, though, he already thinks that the Earth is a sphere. What he recognizes is that the more the Earth is curved, the greater the difference in the lengths of the shadows will be. This leads him to realize that if he were to measure the length of the shadow cast in Alexandria and apply the new type of math that applied to triangles called trigonometry that invented by a fellow by the name of Hipparchus, he could calculate the size of the Earth. So what he did was first he measured the length of the shadow using a gnomon of known height in Alexandria. Using the length of the shadow, the height of the gnomon, and the trigonometric ratio called the tangent on the triangle those two things form the sides of, Eratosthenes was able to calculate that the angle of the sun's rays made with the top of the gnomon was 7 degrees, or roughly 1/50th of a circle, using the Babylon units for circles. He already knew from the observation from Syene that the angle the sun rays made there with the top of a gnomon would be 0 degrees. Now here he has to make an assumption, one first suggested by Hipparchus. The sun was far enough away from the Earth that the rays of light that came from it were essentially parallel to each other by the time they got to the Earth. By the time of this work, most of the estimates of the distance of the sun were pretty big, so the assumption would have seemed like a pretty good one to him. So, if that assumption's true, what the measurements would have meant was that the distance from Alexandria to Syene would have been roughly 1/50th of the distance all the way around the Earth. So, if Eratosthenes knew the distance and multiplied it by 50, actually 51.3, he would be able to determine the circumference of the Earth. Now, this is where the historical record tends to get a lot more murky. The first point of contention is, how did you determine that distance? Carl Sagan claimed that Eratosthenes hired a man to walk the distance from Alexandria to Syene. Others have claimed that he used a commonly known and well-established distance from the records at the library. Perhaps it was both. In any case, the number he used was 5,000 stadia. And herein lies the second problem. We don't actually know how long that stadia actually is. While there were common units of length of measurement in use at that point, it turns out that several of them actually had the same name. The Greeks had what they called an Olympic stadia, and that was about 176 meters in today's money, while the Italian stadia was 8 meters longer at 184 meters. It is possible that he might have used also a more local unit unique to Egypt, where Alexandria was located. Whatever the unit used, it seems pretty clear that Eratosthenes came within about 10% of the actual value, and I've found accounts that place his accuracy as close to 3%. Whatever the actual value we calculated, it's clear that the head librarian in Alexandria had done a phenomenal piece of work that established the size of the sphere within a fairly reasonable accuracy. According to Pliny, this discovery was published as part of a 3-volume book titled Geography. In it, Eratosthenes also draws what may have been the first map of the world known to the Greeks, dividing it into 5 climate zones, 2 freezing regions near the poles, 2 temperate zones, and a single band encompassing the tropics and equator. He also lays out the map for the first time in human history using lines of latitude and longitude. The modern science of geography can be directly traced to this work. Unfortunately, the book has not survived the ages, and so we are left with only references to it in the works of Pliny, Polybius, Strabo, Cleomenes, and Marcianus. Wouldn't it be great if someday an archaeologist using a satellite imagery found some long-forgotten library or chamber buried underneath the sands of some long-forgotten outpost of civilization in the deserts of North Africa, and we could once again read the words of the Pentateuchos as he wrote them? That'd just be fantastic, wouldn't it? The next person to make an estimation of the size of the Earth was Posidonius of either Apamea or Rhodes, depending on the period of his life you're discussing. Living from 135 to 51 BCE, Posidonius was active in Rhodesian politics, wrote on Stoic and Platonic philosophy, studied the history and culture of the Celts and Gaul, and investigated topics related to physics, astronomy, and geography. Like Eratosthenes, he possessed an infinitely curious mind, but unlike his predecessor, he never traveled into the sphere of Alexandria, instead preferring to align himself with the rising Roman Empire due to its promise of stable administration of the provinces it oversaw. That he would think this during the time of the conflict between Marius and Sulla says a lot, I think, about just how unstable the Mediterranean world had to have been at that time. Taking advantage of his Roman connections, Posidonius traveled extensively throughout the Mediterranean, including to the Atlantic coast of Hispania, where his observations of the tides there led him to propose that their daily, monthly, and yearly variations were due to the motions and phases of the moon, along with its alignment with the sun during the equinoxes and solstices. His method of determining the circumference of the Earth took a somewhat different approach than Eratosthenes had. He was aware that from his home in Rhodes, the star Canopus could only just be seen over the southern horizon for a few days each year. However, from observations he made when visiting Alexandria, which he thought to be more or less due south of Rhodes, the star would reach an altitude that was about 7 or so degrees, maybe 7 1/3 degrees, above the southern horizon. As a mathematician of some note, one of his works was a proof of Euclid's fifth theorem. He understood that this difference was due to the Earth's curvature in much the same way Eratosthenes knew that the difference in the shadow angles had been. He then used the same method as his predecessor of dividing 360 degrees by the altitude difference between the two locations, i.e., that's 7 1/3 degrees, and then multiplying that number by the distance between Rhodes and Alexandria, a number he took to be 5,000 stadia. From this, he arrived at a number very close to that of Eratosthenes of 240,000 stadia. The interesting thing here is that we have a number of errors in the determination that are likely due, at least in some part, to confirmation bias. Let me see if I can explain. It turns out that Posidonius' altitude measurement is off somewhat. The true value is actually much closer to 5 1/4 degrees, with the difference likely being due to the refraction effects of the Earth's atmosphere, i.e., its ability to bend light as it passes through. Additionally, the distance between Rhodes and Alexandria was only 3,750 stadia. Using Posidonius' angle and the correct figure for the distance between the two observing locales, the number would have been closer to 180,000 stadia, or about 33% smaller than Eratosthenes' measurement. So why did Posidonius, normally an excellent observer of nature and an exceptional scholar, make the mistake he did? The best explanation is that he already knew Eratosthenes' number and was hoping to confirm it. When his angle measurement came out pretty close to the other man's angle measurement, he probably picked a distance number that gave him a similar answer. This is an historical example of one of the biases scientists have to contend with in their work, the desire to agree with the previous findings of their colleagues. It's understandable that if a well-respected and established figure of the community arrives at a result, a later researcher would expect to confirm their findings. However, this confirmation bias can often lead to the most well-intentioned observer or researcher ignoring important differences. In this case, had Posidonius been more diligent, he would have come up with that smaller number. Had that been the case, perhaps he would have tried to figure out the reason for the difference between the two numbers and realized that light traveling through the Earth's atmosphere at a more oblique angle would have been bent or refracted, and thus he would have made a really important discovery. As an important historical coda to this, when the later Greco-Roman writers cite Posidonius' work, they would report the smaller, corrected value. The most notable among these would be Claudius Ptolemaeus, in his work best known as the Almagest. It would be this value that Columbus would use to convince Ferdinand and Isabella that he could sail across the expanse of the Atlantic to reach the Spice Islands of Indonesia through a different route, something that would allow him to circumvent the monopoly granted the Portuguese by the Catholic Church on the incredibly lucrative spice trade. Following the works of these Hellenistic astronomers, it was well accepted in the Greco-Roman world that the Earth was a sphere. However, as the world of the Mediterranean splintered and the western half of the Roman Empire collapsed, much of this knowledge was lost in places. In the Eastern Empire, as the influence of Christianity grew, there was a period of time when the theological considerations dictated by a literalistic interpretation of the Hebrew Old Testament competed with the accepted model. While figures such as John Chrysostom advocated a flat disc-shaped Earth, the movement soon lost adherents, as the evidence for a spherical Earth was just too great. In the fragments of the Western Empire, various scholars held varying positions, but as texts were rediscovered in various libraries, the spherical model reestablished itself as the dominant one. With the rise of the Arabic Empire, centered on the cultural and religious tradition of Islam, came into form, the practice of astronomy and geography shifted east from the Mediterranean into the Arabic Peninsula. In the early 9th century CE, the Caliph al-Ma'mun commissioned a team of astronomers to determine what the length of a degree along a meridian would be. This group used the length of the meridian between Palmyra and al-Raqqa in Syria to determine that 1 degree of latitude corresponded to 56 2/3 Arabic miles, which also corresponds to being just shorter than 112 kilometers. This gave a value for the circumference of the Earth at 24,000 miles, which is very, very close to the actual value. In the early 11th century, the man who was perhaps the greatest of the medieval Arabic astronomers, Abu Rahan al-Biruni, devised a third unique way to make a measurement of the size of the Earth while sitting at the top of a mountain in modern-day Pakistan. We'll do another supplemental episode on the life of al-Biruni, so I'll leave the details of his life for later and focus on his method here. The story is that al-Biruni was stationed at a fort in a place called Nanadna, 60 miles south of Islamabad, with the Ghaznavid Sultan Mahmud between 1020 and 1025 CE. From his location, he could observe a high mountain to the west that overlooked the flat plains of Punjabi. This, of course, gave him a great idea. What he did is he climbed to the top of the mountain, and he used this instrument known as an astrolabe to measure the angle below the horizontal down to the clearly defined horizon below him. Now, once he knew that angle, what he needed to know was the height of the mountain above the plain. To make this measurement, he used a square board that was marked off at even intervals. He set the bottom of the board on the ground and then elevated the far corner until the bottom of the board sighted the top of the mountain. He then used a plumb line dropped from the top corner to mark a point on the ground behind the corner still on the ground. If you're a bit lost here, we'll post a diagram on the podcast website, thescientificodyssey.typepad.com. Once he had these measurements, he could use the geometry of similar triangles to determine the mountain's height. Once he had the value of the height of the mountain, he could combine that with his astrolabe measurement, said to be 34 minutes of arc, and some more geometry of similar triangles to determine the Earth's radius. He found this to be 12,803,337 cubits, or, in modern terms, 6,339.9 kilometers, which is less than 17 kilometers, or about 0.02%, off the presently accepted value. If you're not pretty amazed that a man sitting on a huge globe could measure the size of that globe with such phenomenal accuracy, I'm not sure you truly are grasping how hard a task that really is. As we'll discuss in a later show, the history of medieval Arabic astronomy is replete with similar stories of brilliantly subtle thinking and a dedication to painstakingly accurate measurement. Throughout the Middle and Late Medieval period, we have a number of instances of various scholars referring to a spherical Earth. These include Hildegard of Bingen, who is, by the way, a truly amazing figure, Johannes de Scarsbosco, and Honorus Augustodunus, who wrote a primer for young clergy that explicitly taught of a spherical Earth. Dante, in his Divine Comedy, represents the Earth as a sphere in his depiction of the relations of heaven and hell to the realm of men. Of course, as we've mentioned, Columbus represented the Earth as a sphere in his presentation to the Spanish monarchy, and Ferdinand Magellan's entire voyage both presupposed and provided direct evidence for the spherical nature of the Earth. So why is it that many of us learned in school that Columbus was among the first to suggest that the Earth was a sphere, and that most of his contemporaries didn't share his view? While the reasons for this are complex, let me see if I can untangle it all a little bit. It is true that there was a small group of individuals in medieval and Renaissance Europe that held the Earth to be flat. Just as was the case with Chrysostom in the 6th century CE, the basis for this belief was a very literal reading of the Hebrew Scripture that inferred that sort of a conclusion. And while this view may have been shared by some percentage of an uneducated peasantry of the time, almost all of the learned figures would have understood the true shape of the Earth as being a globe, based on all of the things that we've already talked about. What seems to have developed from this was a practice of jokingly referring to someone who was unlearned or lacked intelligence as believing in a flat Earth. In other words, it was a form of intellectual mockery, similar in the vein of, "Gosh, I can't believe Dr. Smith thinks that God would have mercy on an infidel. I'll bet he thinks that the Earth is flat too." Here in the United States, the thread of the myth can be next traced to, of all people, Thomas Jefferson. A noted deist who looked upon the exercise of authority in both organized religion and government with skepticism, Jefferson wrote in his Notes on the State of Virginia, quote, Government is just as infallible too when it fixes systems in physics. Galileo was sent to the Inquisition for affirming that the Earth was a sphere. The government had declared it to be as flat as a trencher, and Galileo was obliged to abjure his error. This error, however, at length prevailed. The Earth became a globe, and Descartes declared it was whirled around its axis by a vortex." Unquote. As we will discuss in a later episode, this is most certainly an inaccurate description of both the events that took place and their causes, but it fixed the idea in the minds of many. In 1828, Washington Irving wrote an account of the life of Christopher Columbus titled A History of the Life and Voyages of Christopher Columbus. This work was meant to be a highly romanticized telling of the explorer's life, but due to Washington's intellectual standing at the time, it was more often taken to be a scholarly work. As part of the description of the meeting between Columbus and Ferdinand and Isabella, Washington describes a faction of dissenters associated with the Catholic Church who criticized the navigator's plan by saying that the Earth wasn't a sphere. A few years after this, in 1834, French academic Jean-Antoine Latron published a work on the cosmographical ideas of the Church Father that either selectively picked out those figures, the very few of them, who advocated for a flat Earth model, or misrepresented the statements and importance of others. Latron was a virulently anti-religious figure in the post-revolutionary landscape of France, and his work is broadly recognized as a polemic against the restoration of the Church in French society. Following this, a number of other historians, including William Whewell, and most importantly in the United States, chemist John William Draper, followed suit for a variety of reasons. In almost every case, the instance of a broad medieval acceptance of a flat Earth model was based on the writings of just one or two marginalized figures far from the main current of intellectual thought. Additionally, there seems to have been a desire to sharpen and focus the narrative that pitted the forces of religion against those of science in a classic good versus evil or David versus Goliath way. Here in the States, we continue to reap the bitter fruit of this false dichotomy, planted and nurtured by individuals in both camps. Eventually, this view began to make its way into history texts used in elementary and secondary textbooks and began to be seen as something of received truth. In the 20th century, there began to be a swing back towards historical accuracy, with works published by C.S. Lewis, Geoffrey Burton Russell, and Louise Bishop, all of whom documented that most thinkers of the period after 1000 CE accepted the idea that the Earth was a sphere. Unfortunately, this myth remains a persistent inclusion in compulsory primary and secondary education. A survey of German and Austrian school texts found it to be prevalent in 2009, for example. If there's one thing I hope you can take away from this podcast, it's that Columbus proving the Earth was round is a complete and total myth. As a final note on this topic, one of the most ambitious projects of the late Enlightenment involved the measurement of the shape of the Earth. Isaac Newton's work on gravity had led him to suggest that the Earth was not a perfect sphere, but rather what we call an oblate spheroid. In other words, he said that because of the Earth's rotation, the sphere would be slightly flattened at the poles and wider around at the equator. This view was shared by his continental colleague, Christian Huygens. On the other hand, the astronomer Jacques Cassini had claimed that the opposite would be the case, with the Earth being stretched at the poles and squashed at the equator in a figure known as a prolate ellipsoid. Cassini's view was based on the meridian measurement he had made between Dunkirk and the Spanish border in France that showed that the degree length measured on the northern segment between Paris and Dunkirk was shorter than one measured south of Paris. The French Academy of Sciences commissioned a study to be performed. 2 expeditions, known as the French Geodesic Mission, were sent out to 2 points. One as far north as possible in the Torn Valley in Finland, and the other at the equator in Ecuador to measure the length of a degree in each location. These measurements established that Newton was correct and that the Earth is in fact a flattened sphere. This did not, however, bring the issue to an end. During the French Revolutions, one of the reforms that was undertaken was a regularization of the units of measurements to be used. One of the underlying causes of the economic crisis that had gripped the Ancien regime was a lack of standardized units at the time of the calling of the Estates General in 1788. As the revolution progressed, it was decided that all of France should use the same set of decimal-based units of length, mass, and volume. It was also decided that these units should be based on something that belonged to all of humanity in that spirit of equalité, liberté, and fraternité. As such, it was decided that the length unit would be based off the measure of the Earth itself, and so the meter was defined as 1/10,000,000th of the distance from the equator to the North Pole. A scientific expedition was then sent out to measure the 45-degree piece of the meridian that ran from Barcelona through Paris to Dunkirk, meter by meter. To get a sense of the difficulty of such an undertaking, it should be realized that the scientists had to cross 2 mountain ranges, miles and miles of dense forests, and a number of other geographical obstacles. And they had to do this all during a period of intermittent military conflict and political instability that threatened to not only terminate the endeavor, but also the lives of the men that undertook it. For those who are interested in a full account of this project, let me recommend Ken Alder's excellent book, The Measure of All Things. It's a really wonderful sort of description of all of the things that had to go on for this expedition to happen. The result of the effort was to determine the meter to an accuracy of about 3 sheets of paper stacked on top of each other. It also established, to an unprecedented accuracy, the amount of the Earth's oblateness. Finally, the other thing to come out of this project was what Alder claims is the final piece that makes science science. One of the things that really bothered the two scientists who were in charge of the expedition when they got back to Paris to analyze the data that would be presented to the French Academy was that it didn't completely and precisely converge to a single number. They had used theodolites that had been specifically designed and constructed for the project that were by far the most accurate ever developed. However, the data didn't yield results that approached the level of precision that the theodolites should have allowed. And so they ended up settling on a number that was slightly off the actual value that I mentioned. So what happened? For a time, while there were ways for a scientist working with a large body of data to determine the effect of random uncertainties that might arise during the data-taking process, they were pretty rudimentary, and they were not able to handle cases where there might be several factors that might contribute to the uncertainties, as would have been the case in making the surveying measurements required of this particular project. As a result of this problem, there were 2 consequences. The first was known as the development of a least squares method of data fitting and analysis. The second was the recognition by the scientific community that there would always be error and an uncertainty in the process of measurement that would need to be characterized if scientific work was to be considered trustworthy. One of the theses of Alder's book is that this change is the final piece of scientific practice that had to fall into place to create what is truly science out of what had been natural philosophy. While the dividing line isn't as sharp as some claim, it is certainly at around this time that researchers go from being called things like savants or philosophers or natural philosophers to being referred to as scientists. I hope you've enjoyed this brief digression into the history of humanity's understanding of the shape of the Earth. As always, this should only serve as an introduction. There are a number of other tangents one can follow from this topic, including the absolutely fascinating topics of celestial navigation and spherical trigonometry. While it may seem that modern technology makes these topics merely esoteric in their application, it should be noted that the United States Navy has reinstituted both topics into its curriculum, with the understanding that while the technology may fail, the shape of the Earth and the map of the stars above it never will. For those of you who aren't tired of the sound of my voice yet, and who might be interested in a more wide-ranging and free-flowing conversation on the history and philosophy of science, I recently did an interview for the Dan and Glenn Show. It was a great conversation, and I'll put a link to the episode on our website and on our Facebook page. I'd like to thank Glenn and Dan for their hospitality. Their show is an interview-based podcast with the occasional Shooting the Breeze episode thrown in for fun. I do want to provide the warning that while the show we did was clean in terms of both subject matter and language, some of their episodes can contain profanity, so if you're sensitive to some things, you might only want to listen to the one that we did. If not, and the show concept seems interesting to you, head on over and check them out. I'm sure you'll really enjoy what they've got to say. In our next episode, we'll return to our cosmological narrative and look at the work of the Hellenistic astronomers of the Greco-Roman world. Until then, full sails on your journey.